Okay, well the problems, excuse me, the problems in this section are going to be pretty much the same every time. Every one of these problems is going to get very, well, not all of them, but like 80, 90% of them. It's going to be very repetitive. We're just going to draw that normal curve, that bell curve thing every time. Put the middle line on, 3 jumps to the right, 3 jumps to the left, the same percentages every time. And then we're going to fill in the number. Remember the numbers on the bottom change from problem to problem, but the percentages never change. So it's going to be kind of the same thing every time. So here we go. So just know that in advance. You know, they go blah, blah, 2,500 students take a college exam. The scores have an approximately normal distribution. When you read those words, that means the bell curve fits. That's what it means. This comes up a lot of times in real life. When they say such and such happened, and the results, the scores, have a normal distribution. It means normal, like in the way we use the word normal, and the normal is the bell curve. That is normally what happens when a bunch of people take a test, or you measure the width of a bunch of trees, or the height of a bunch of 7-year-old girls or boys or whatever. Normal distribution, bell curve. So here we go. I'm going to draw a bell curve. In fact, I think I'm going to draw one on a fresh screen here so I have more room. So bell curve. And you're going to have this big bell curve on your 3x5 card, and it's going to be the key to about 70, well, it's exaggeration, 50% of the test. Like half the test will be all about this bell curve. So 3 lines to the right, 3 lines to the left. And I'll do the percentages right now because those are always the same, right? They never change. 34, 34, 13.5. 13.5, 2.35, 2.35, 0.15, not even 1% there at the end, 0.15, 0.15. Okay, now, those are always the same. That never changes. But what changes is the numbers on the bottom. How do we do the numbers on the bottom? Well, in the very middle goes the middle. What's that? Well, this is the middle, isn't it? It's saying the mu, like that funny-looking little Greek lowercase m thing, is 56. So, is that 56? Yeah, not 58, right? 56? Yeah. So put that right in the middle, like that. There's the 56 right in the middle. And then how much does it go up from line to line? Well, whatever that sigma was, what was that? It was 9. Right there, the sigma's 9. So you just add 9, add 9, add 9 to the right, and subtract 9, subtract 9, subtract 9 to the left. So I'm just going to add 9. So adding 10 would be 66, so back up 1, 65, huh? Easy way to add 9 is add 10 and subtract 1. So then add 10 again, 75, and subtract 1, 74. So add 10 again, 84, back 1 up, 83. So I just add 9, add 9, add 9. See what I did there? Put the middle on, plus 9, plus 9, plus 9. And then to the left, minus 9. So that'd be minus 10. 46, add 1, 47. Minus 9 again. And minus 9 again. There we go. Now we'll answer all the questions based on this. This will be the key to every question they want to ask me in this problem. Everybody good with how we make that? It's going to be kind of the same every time. All right, let's see what their questions are. They're saying, estimate the average score on the exam. So what's the average? Well, that's the middle. That's the 56, isn't it? Yeah, 56 right there. So there's the middle. That's 50. Oh, I've already got the answer, don't I? Okay, approximately what percentage of the students score 56 points or less? Which percentage of the students... And you can see my answer is there. It's already 50%. See why that is? What percentage of the students get a 56 or less? Well, that's half the curve, isn't it? If you added up these percentages, right here, 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 and here, they make 50% because they're half the curve. So I'm not going to bother to type them into my calculator, right? So they asked, what percentage of students got 56 or less? Less always means to the left, more means to the right, huh? So 56 or less, 50% of the students. So that's that question. Next question. Approximately what percentage of the students got between 47 and 65. 47 and 65. Let's see it. 47 and 65. So here's 47 line. Here's the 65 line. What percentage got in that zone? Well, these percentages, huh? See how easy it is once you have the whole curve made, the numbers in the bottom, you just go to what they're asking. 47 to 65, boom, 34% and 34%. So add these up, that's 68%, isn't it? And that's the answer there. Finally, part D. What percentage of students scored 65 or more? 65 or more. So here's 65 or more, which means to the right, doesn't it? Isn't that shading I just did? 65 or more. More means to the right. Less means to the left.
So you add the three standard deviations on the end?
You just add these three percentages. It adds up to be 16%. If you add those up on your calculator, it'll be 16%. And that's the last question on that, last part of that question. Is that good? It's going to be really similar to this every time. It's going to be draw the curve, put the numbers in the bottom, percentages never change, then they'll ask you questions back and forth. Is that good? And so that was 16%. By the way, they never did, but they will in the next couple of questions. They'll say, they'll instead of saying what percentage of students got whatever, they'll say how many students. How many students. How do you go from a percentage to how many actual people that was? Exactly. So if they said how many students instead of what percentage, I would make that a decimal point 16 and multiply by how many total students, which is, I saw it, 2,500. Yeah, there it is, 2,500 students. Does that make sense? Like if I said, hey, 20% of this class is going to get an A in the end, and there's 30 people, how many actual bodies is that? 20% of 30 people would be 0.20 times 30, with it, 6 people. Make sense? So whenever you want actual people, change to decimal, multiply by the total number of people. That's how you find actual people. So that's what they're going to ask us in a minute. So it's hardly different. You just take the percentage, make it a decimal, times 2,500. So it's no big deal. All right, good. Questions I can answer on that? All right, it'll be the okay, so part of research project, blood pressure, 3,000 patients, hospital recorded. Systolic blood pressure given in millimeters, have an approximately normal distribution, mean, boom, boom, boom. Oh, this little thing right here, when they say use the 68, 95, 99.7 rule, that means the bell curve. Why does that mean the bell curve? Let me show you why. If you add up these two numbers in the middle, you get 68, right? If you extend that a little wider and add up the four middle numbers, guess what you get for the four middle numbers? 95%. And if you extend it even further and do the six middle numbers even wider, you get 99.7%. So that's where they're getting the 68, 95, 99.7. That's 2 boxes, 4 boxes, 6 boxes in the middle added up. That's their fancy way for them to say use the bell curve. That's all they're saying. Does that make sense on that? So getting back to here, when they say use the 68, 95, 99.7 rule, they mean use the bell curve. Use the bell curve, which is what we're going to do. All right, so can we do this one? Let's draw the bell curve. Make a little more room down there. Let's draw the bell curve. One line in the middle, 3 jumps to the right, 3 lines to the left. You know the percentages, they never change. 34, 34, 13.5, 13.5, 2.35, 2.35, 0.15, 0.15, okay. Now, so the percentages never change, but the numbers on the bottom do change. Can you put the numbers on the bottom in? So start with the middle. What's the middle going to be? The 127. Yeah. So the 127. Oops. And then that's the middle line. And now how do we get the 3 lines to the right?
You add 13.
You add the standard deviation. So you add 13, add 13, add 13. 140, 153, 166. Is that right? Add 13, add 13, add 13, like that. And then to the left, you subtract 13 3 times. So I'm going to get 114, 101, and 88. Is that right? Yeah. We good there? Everybody see how I did that, just like we did last time? It's like the same kind of question. Now they say, estimate the number of patients whose blood pressure was 114 or higher. 114 or higher. Can you do that? Let me give you a second on that. All right, so 114 is right here. So 114 or higher, that's what it says, right? 114 or higher. Which way is higher, right or left?
Right.
So from that line to the right. Making sense so far? If they said lower, I would have went to the left. So they're asking me, what do all these percentages right of 114, higher than 114, add up to be?
84%.
Yeah, well, all of these must be 50% because they make up half the curve, don't they? I don't want to bother typing those all into my calculator. They're half the curve. They got to be 50%. And then this is another 34, so it's 50 plus 34, it's 84% to the right. Not quite done yet, but almost. Is that good so far? Everybody see that? Right? 114 to the right of it, it's 34, and then this is 50. Because it's half the curve. 34 and 50. 84%. 84%. Now, they didn't say what percentage, like they did on the last problem or 2 problems ago. What percentage? They said how many patients, how many actual people. So remember what we do? We take that 84%, make it a decimal, and multiply by the number of people, which is 3,000, the total number. So 0.84 times 3,000 comes out to be 2520. That's how we got that answer. Does that make sense? How many to the right? How many more than 114? 34 and 50. 84%. Make it a decimal times 3,000 total people. 2,520 patients must have a blood pressure of 114 or more. That's what that means. You know, real life. And I'm sure blood pressures are normally distributed. I'm sure this is very true to reality. That means you know if you have 3,000 patients with an average blood pressure of 127, standard deviation 13, you would know exactly, I mean very close to exactly, that out of 3,000, 2,520 would have a blood pressure of 114 or more. That's how precise the normal curve lets you predict things. All right, how about question B? How many have a blood pressure between 114 and 153? Excuse me. So if you want to go 114 to 153, it's this one, and that one added up, isn't it? Everybody see that? Those 3? How we doing? Is making sense? So between 114 and 153, 34, 34, and 13.5. Add up those 3 percentages. So 34, 34, and 13.5, 68, 78, 80. Is it 81.5%? That's the percentage, and now they actually asked how many patients, so now I got to make that a decimal. 0.815, right? You always go back 2 places, times 3,000 total patients equals 24.45, which is the answer we got. Johnny.
Did that just register? Did that make sense? But I was trying at first to do minus m times the 675. Why was I doing that? What was that?
Oh yeah, the 675 thing, that is for quartiles. Q1 and Q3. Yeah, that other formula, yeah, like the last problem. Right here. That's quartile. Now, well, how do you know when you're supposed to do that? Well, they explicitly said so. See, they said estimate the first quartile. So then I knew they wanted Q1 and Q3. And so if they just say it straight out, give me the quartiles, then we just use the Q1, Q3 formula. Or if the percentages, instead of being 34, like they're 25 or 75,
Just said that.
that's when we do the quartiles. Yeah, so if they do those things, we do quartiles. Otherwise, we just do it this way. Good. Other questions? Making sense? It's going to be kind of the same every time. Kind of nice about this chapter. It's kind of the same. You can get really good at it because after a while, you've got it. Just same thing. So here we go again. Blah, 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 blah. Use the rule. Blah, blah, blah. Normal curve. Same thing again. I'm going to draw the normal curve. Middle, 3 jumps to the right, 3 jumps to the left. The percentages are always the same. 34, 34, 13.5, 13.5, 2.35, 2.35, 0.15, 0.15. All right. Now, the percentages are always the same, but the numbers on the bottom change from problem to problem, right? Whether you're measuring blood pressures or what's this, weight of foods, normally distributed. So what goes in the middle, on the bottom in the middle?
24.
Yeah, they're telling me it's right here, 24. And how much does each line go up by? 0.75. So this will be 24.75. This one will be 25.5, and this one will be 26.25. And this one will be, what is it? 0.75. So 23.25. This one will be 22.5, and this one will be 21.75. So I just took the middle of 24 and I just added 0.75 3 times to the right and subtracted 0.75 3 times to the left. See how that's the same thing every time? Just bell curve, middle, add to the right, subtract to the left. And then they're going to ask you questions that are kind of the same. So what's the chance, whatever, same thing as probability. What they're basically saying is manufacturing plants, there's so many things in real life that do this normal distribution thing. In this case, the example is manufacturing. In like Frito-Lay manufacturing plants, when they package bags of chips, right? The bags of chips say they hold 24 ounces. Well, really that's the average. 24-ounce bag of chips, they're not exactly 24. The machine isn't exact, but it drops in about 24 ounces. Well, there's a little variation. Sometimes you get a little extra chip. Sometimes you get a little less. The variation, in fact, the average variation, that's what sigma is. How much is the typical bag off of the average by 0.75 ounces? And so basically this will tell you the percentage chance that you're going to get a bag of chips. They're saying, so if you get a bag of chips at Frito-Lay, what's the chance that the bag weighs between 22.5 and 25.5? 22.5 and 25.5. Can you do that first one? Can you answer question A? Using the bell curve there. Just making sense. So 22.5, fill in that line right here, and 25.5, that line right there. So we're talking about this, and this. Just add them up. Does that make sense? Add those up, and it comes out 95%. That good? All right, how about question B? What's the chance, they're saying on B, what's the chance you grab a bag of chips and it'll weigh somewhere between 24 and 25.5 ounces? Part B. So 24 and 25.5. So here's 24. Here's 25.5. So it'd be 34 and 13.5. Just add those up. You get 47.5. This making sense? Am I going too quick? This good? And then part C. The chance the bag weighs less than 25.5. Less than 25.5. So where's 25.5 right here? And less means which way, right or left? It means and less means all the way down, huh? And more would be all the way up, right? So when they say less than 25, you're saying, what's the chance I'm going to get a bag 25.5 ounces or less? It means all the way up. So you got to add up all the percentages to the left of the 25.5 line. So that would be all these percentages. But what's the easy way to add all those up? We don't want to do every one of those in our calculator because we know from the middle over is 50%, huh? So the quick way to save time would be to say, look, I know all of these make 50% because they're half the curve. And then I need these two also. So 50% plus 34 plus 13.5. Add those three up, 87.5 or 97.5. Is that good? That means if you grab a bag of chips at the store, the chance you're getting, it says 25 ounces. It won't be exactly 20 or 24 ounces. The chance you'll get 25.5 or less is pretty good. It's a 97% chance. So every now and then you might get more than 25.5 ounces, but it's rare. That's how they control manufacturing processes. That's one of the measures of it, is they use statistics like this and bell curves. So real things don't always come out, excuse me, the same every time. By the way, this is how you guys know, I mean, it's kind of famous now, right, that the foreign cars, especially those from Japan at first after World War II especially, were better made than the American cars, right? I mean, that's why I have several Toyotas and not a lot of Fords. I gave Ford a try one time, and it went miserable. I bought a Ford family van, the Windstar. Was that 10 years ago, maybe 15 years ago? Anyway, I won't waste you with my long stories, but that thing cost me, I didn't buy it new. I bought it used off of a rental car lot, but anyway, I mean, I looked at the Toyota vans, and I thought, oh, they're more. I don't want to spend that. I don't got, I have one income, a bunch of kids. I can't be going for that Toyota thing. I'm going to go for the cheaper Ford Windstar. And I know they're not as reliable. I read the reliable ratings on the internet, and I know it's going to cost me a little money in repairs, but I'm saving money on the purchase, so I'll save that. Oh, it was worse than I could believe. I bought that thing with 30,000 miles. Within 1 year, the computer had gone out. It only had 30,000 miles on it. The computer went out. I can't remember what else. I was constantly at the shop. And like the third time, they told me all the O2 sensors are out. The computers, it's going to be $3,000. The Ford dealer is just taking my money. And I was like, all right, fix it. And then I did the cardinal terrible thing to do with the car. I traded it into the dealer. You never do that. They kill you. They just kill you. They just give you nothing for your car and resell it at twice the price. And I knew it, but I thought, I can't sell this to somebody. I hate this car. I just couldn't do that with a good conscience. So I said, look, fix it. And then I went back and I traded it in. Anyway, and I got a Toyota. And I got the what's it called, the Sienna. And I bought a second one. I've still got the first one. It's got almost 200,000 miles on it. I even towed my old little Toyota Corolla behind the Sienna across the nation to Kentucky and back. And I haven't lost a transmission. I will never deviate from Toyota again. Never. I remember I called the Ford Windstar plant one time because when I was having all these troubles. And the lady that answered the phone for Ford Windstar, she answered the phone and she said, hello. I said, yeah, I have a question about my Ford Windstar, about something on the... She said, oh, the Ford Windstar. It's a very reliable family vehicle. She said it just like a salesperson, you know. I felt like saying, and she said, a very reliable family vehicle. I felt like saying, compared to what? Are you kidding me? But I didn't. I just said, okay, yeah, well, let's talk about... Anyway, so, all right. Oh, I said all that for a reason. Do you know why? You know why that the manufacturing was better? Now a bunch of the Toyotas are made in America. It's all kind of the same thing. But at first they were made in Japan, and Japan's performance in manufacturing processes greatly excelled ours because of statistics. It was exactly this. I really did have a math application with all that. It was statistics. There was a guy named Deming. I'm into history. I like real life people and what they do and accomplish and things like that. Maybe I'll just show you his picture if I can find it. Anyway, Deming was the hero in Japan. Well, he's actually an American guy, but he's the one that used statistics to improve. Wait a minute, where is he? Mr. Deming. Oh, it's at the end. So he's the one that improved. Oh no, they put Gauss back here? When did they change to Gauss? Let me see. Maybe it's chapter 15. Sorry, I'm wasting all your time. All right, well, it's Deming. I can't find it right now. But his name is Deming. And they actually, so what he did, Mr. Deming, he had a physics degree from America. He had a PhD in physics. But he ended up going to Japan and helping them in the 50s and 60s, right after World War II, when they were rebuilding their nation. He helped them with their manufacturing of cars. And he showed them how to make things more constantly regular. Do you realize that's the problem with cars built badly, right? Because things have to fit well and run down the road for hundreds of thousands of miles without a problem. Well, if there's a lot of variation, like if on Monday the temperature in the factory gets hotter, then Tuesday it gets colder, metals expand with heat and shrink with cold. And so if you've got a lot of variation going on, then you build certain parts bigger, just a little bit's all it takes. One day, smaller the next day. When you try to fit them all together later, they don't fit as well, right? Unless they were exactly the same every time. And you got to control a lot of things, like the temperature in the factory, the humidity in the factory, the way the workers do everything exactly the same. Well, that was more controlled with statistical analysis to make everything much more constantly the same. Deming used that to give guidance to the factories in Japan to produce cars that were more reliable because the pieces fit better. There was less up and down. There was less variation than what was going on in America. He offered his services at first to America. No American manufacturer would have him. So he went to Japan, gave them advice, and the Japanese industry took off, as you know. And he became a hero. Like literally, he's like a folk hero. And you can type in Deming, manufacturing, and they actually made an award for all manufacturing in Japan. They called it the Deming Award, and for excellent management of corporations. Like he became a folk hero in Japan. And finally, it was in the 80s that America recognized it. NBC did like a big special on it. They said, they did about how Deming had improved overseas manufacturing. They did this big expose about how he used statistics to improve their processes. And after that, then, sure, Ford gave him a call. Chevy, after that special was aired on NBC in the 70s or 80s, all the big manufacturing in America gave him a call, and he came out and gave them advice as well. Anyway, he was a folk hero. He used statistics to improve processing. Because things vary, don't they? Even the bags of chips, things go up and down. They're not always the same, even when machines do their thing. Maybe one more. Maybe there's a small difference. I don't know. So blah, blah, blah. Same thing. There's the middle. There's the jump. Percentile. Yeah, be good if I say it's really the same, but they're going to try to trick you with a different word. It's the same. So, yeah. So put the middle on. 3 jumps to the right. 3 jumps to the left. The percentages are always the same. 34. 34. 13.5. 13.5. 2.35.15. 2.35.15. Okay, so there we go. There's the percentages like usual. Okay, the middle is the 15.75. And every jump to the right is 3. So this will be 18.75, 21.75, and 24.75. So I put the middle on, add 3, add 3, add 3. Other direction, subtract 3. So this will be 12.75, 9.75, 6.75. Same thing, right? Nothing new there. Now here come the questions. 9.75 pound baby girl is in what percentile? Now, if you go to if you had a baby, they give you their percentile weights at every checkup. So newborn, they say your child's at the whatever percentile, and at the 3-month appointment and 5-month or whatever it is. I forget now. All my babies are big. But what does percentile mean? Let me give you the definition of that word. And this is exactly what doctors are working off of, is this bell curve. All that's based on this bell curve. So percentile. It's almost like percentage, but it's a little different. We haven't talked about it before, have we? I can't remember. I don't think so. Percentile means percent to the left. Percent below, in other words. So really important that you know that word. For the next exam, there'll be a few questions, but also real life. Real life, they talk about percentile all the time. If you want to be an educated person, they can talk about, I don't mean you got to calculate something with your calculator. I just mean know the real life meaning of that word. A lot of people in business and social science and, even just taking your kid to the doctor or reading results in the news, they'll use that word percentile all the time. And it's not exactly the same as percentage. It's close. It means percentage to the left, percentage below. So for example, suppose you go take the SAT or any of these big standardized tests. They always give the percentile score. So suppose I go and I take the SAT test and I say, hey, I got at the 60%. What if my results come back and it says you got 60 percentile, not percentage, but percentile? What does that mean? Is that a good result? If my kid comes home and says, yeah, Dad, I took the SAT. They told me I was at the 60 percentile. Should I say, yeah, dummy, you got a D? What do you mean you got 60%? No, it doesn't mean that. It's not 60%. Is that a good result? Is that better than average or worse than average? Better. Because remember what percentile means? 60% are below. So that child's above average. Right? 60 percentile means percent below. That means among all the people that took that SAT, 60% of them, more than half, got below. So that's a good score then. So that means at least it's above average. Does that make sense? It's percent below. So if 60% got below you, what percentage got better than you? 40%, right? I mean, you're in the top 40%. 60% are below you. So that's a good score. I mean, this is above average anyway. Good? Is that making sense what percentile is? So they're going to ask us some stuff about 9.75 pound baby girl is at the 2.5th percentile. No, what does that mean? What does percentile mean again? When it tells me, actually, that's the answer, huh? So here's the question. I'm jumping to the answer. Let's start with the question. 9.75 pounds. Where's that? Right here. And they're asking me, what is the percentile? Meaning, what is the percent below? What is this and this add up to be? Does that make sense? So whenever they give you a thing and then they say percentile, they mean add all the percentages below. Add all the percentages to the left. So 2.35 and 0.15, right? $2.35 and 15 cents make $2.50, don't they? Good so far? Let's try the next one. How about part B? A 21.75 pound baby girl. 21.75, where's that? Right here. So what are all the percentages? And they want percentile. So they want all the percentages below. So they want this and this and this and this and this and this. Don't they? Does that make sense? Percentile. So what's the easy way? Whenever you have the whole half, is just to say, look, these guys are 50%. And 34 and 13.5. That's 97.5. Make sense? Percentile, percent below. Final one. Baby girl, 75th percentile. There's the trick question. are we going to do this one? So baby girl, 75th percentile. What's that? Which formula? Those other ones, huh?
Yeah.
Right on. Good job. Exactly. What's supposed to flash in your mind when you see 75 or 25? Q1, Q3. Yeah. Forget about this normal curve. This is a Q1, Q3 question. See how they snuck that in? But you're on the alert now, right, for the exam next Tuesday? 75, 25. You just say Q1, Q3. They're giving me a Q1, Q3 right away. So now, which one is it, though? Q1 or Q3? Well, 75th percentile. What if I say, I took the SAT, I got 75th percentile. What does that mean? Am I above the middle or below the middle? Above. 75% got below. Remember, percentile means percent below. So that means above the middle. So that's Q3, isn't it? That's Q3. So it's for sure Q3. So you just grab the old Q3 formula, which is mu plus 0.675 sigma, and the mu, the middle, 15.75. Notice I'm not even going to use the bell curve at all. When they give you 75, 25, you just use the Q1, Q3. Don't use the bell curve at all. What's the sigma? They told me somewhere up here, 3. Hit the buttons on your calculator. I'm sure you get 17.8. Does that make sense on that? So when you go to the doctor, that's what they're trying to make sure your child is healthy, basically, right? So they tell you your child's weight and height compared to other boys or girls at that age. There's a different chart for boys versus girls. So they'll say, newborn babies are supposed to be, there's an average, but some are lighter, some are heavier, As long as you're in the general spectrum, they assume your child is healthy. Make sense? We had that, my first baby girl, this exact problem. My second child was my first girl. Emma girl, she was born crazy light. Like, she was like 1%, just completely healthy. But she's still super tiny today. She just went away to college a few months ago. She's super tiny. But anyway, the doctors thought she was unhealthy. Exactly the same reason. That they use these charts to measure health. And so Emma girl was so light, she just always has been. She was below the 1 percentile. And then we took her into a doctor visit, just a regular checkup. And I think the doctor actually nicked her with, it was a young doctor with her little thing, and there's little blood in her stool. I think it was just the doctor's mistake. And the doctor saw the blood, knew she was at 1 percentile, and shipped us off to San Francisco, where they have all those children that have really sad things, So they thought she had a serious problem, so we took Emma girl there. They put her under all those machines all day long, and everything was fine. We came back. It was a young doctor, and she was really apologetic. We were like, no problem. We're thankful that you were careful. But anyway, that's how they measure. That's how they measure health. If you're really low or really high, they think something's wrong, because there's this normal result that you see for babies' weights. So lots of applications, real life. This guy. All right. So honest coin. Yeah. So basically, if you flip a coin a bunch of times, if I take a coin and flip a coin, if I flip a coin 10 times, how many heads do you think I'll get? I mean, who knows? It's random. But on average, 5, about half, right? Because, it comes with heads usually about half the time. Right, that's exactly right. So if you flip the coin 6,400 times, how many times you get heads? About half. So it turns out if you flip a coin a bunch of times and you record the results, you know what you'll get? You'll get the bell curve. I mean, there's just endless applications of this thing. It's true. This is how casinos operate. It's not as random as you would think. Basically, you should know if you're going to go gamble, you will lose money. It's a science for them, which is fine. If you want to lose your money that way, if that's fun entertainment for you, great, do that. But know you're going to lose. Don't. You know who they get is people that think they're going to win. Don't think that. That's a mathematically stupid thought. I don't mean to be crude, but I want to plant clearly in your mind, you will not win. That's like thinking I can jump off a cliff and overcome gravity like the Roadrunner used to do, right? Right? No. You might think, yeah, but my uncle had a lucky week. Oh, sure, anybody can have a lucky day, lucky week, maybe even a lucky year. But if you keep at it enough, the laws of probability will take over. They've calculated all in advance. It's all based on the normal curve. The number of rolls of the dice, probably this, probably that, and all the games are figured out. It's a science for them. They know they can tell you exactly how much they're going to make per hour. They've got it so well calculated. So anyway, just know that. Don't be suckered in. If that's great entertainment, you like doing that for entertainment, great. But don't think you're going to make money that way. You will not make money that way. They will win. All right. So I always have people that tell me, no, I've got it. My wife's uncle and aunt, they swear that they win money. And I've stopped bugging them over the years. But, I'm like, no, you don't win money. You don't. I know better. I know the math. But anyway, they don't. Anyway, I love them, but they don't agree with me on that topic. They're funny. They crack us up. Okay, anyway. So it's a bell curve. So if you do any kind of random thing, roll a die, flip a coin, anything that's supposedly random is really not as random as you would think. There's a bell curve result. And the average will be the 3,200. Let me give you the formulas for that. The average is N times P. N is the number of times that you do whatever you're doing, flipping the coin, rolling the die, whatever. P is the probability each time. P is the probability each time. So in other words, on this problem, if you're flipping a coin, what they said we're going to flip it 6,400 times. There it is. N is 6,400. So 6,400 times. Every time you flip a coin, what's the probability of getting heads? Or they're saying tails. Whatever. It's the same thing. It's still 50%, isn't it? Y'all with me? 6,400 times the probability of tails, which is 50%. That's half. So it just comes out half of 6,400, 3,200. That's how we got that first answer. Good so far? So that'll be the middle of the probability number of tails curve. And sigma, the standard deviation, here's the formula. This is another formula. So you need this formula that I just gave you right here for your 3x5 card. Mu is N times P for any random activity. And what's the next one? For sigma, it's square root of N times P times 1 minus P. All inside of a square root. So you need those two formulas. I'll box them both. Both those two that are in boxes, you need those two formulas for the next exam. There'll probably one, maybe two questions for something random. Yeah?
So we only use that for like chances, like probability?
Yeah, anything random. That's right, probability things. Rolling dice. It'll probably be dice or coins. Probably one of those two. So, square root of, here we go, N. So we're supposed to do N. What's N? That's right here, 6,400. Times P, so this is N, times P. P is still 0.50. Times 1 minus P. 1 minus 0.50. Y'all good to there? So I plugged everything in. Can you crank that on in your calculator? You should get the square. The inside number should become 1,600, and the square root is 40. That's how we get the sigma. Want to make sure you can do that on your calculator? 6,400 times 0.50, and 1 minus 0.50 comes out to 0.50, doesn't it? This right here comes out to 0.50. So in the end, it's 6,400 times 0.50 times 0.50, which is 1,600. Square root it, 40. So what that means, now that we have that information, yeah.
The 0.50, that's the probability, like...
That's the probability of getting tails. Every time you flip a coin, the chance you'll get tails is 0.50. Chance of heads is also 0.50. Yeah. So for example, good question. Glad you brought that up. What if they said, hey, you're playing craps and you're going to roll the dice, and let's just make it simple. Let's just do one die. If you're going to roll one die, what's the chance of getting a 3, for example? 1 out of 6, right? Because there's 6 different numbers, 1 out of 6. So then the P would be 1/6 in that case. So if we're rolling a die, the probability would be 1/6. If we're flipping a coin, the probability is 1/2 or 0.5 decimal. Does that make sense? The probability of whatever it is you're doing times the number of times you're doing it. So N times P, that'll be your middle. And then the square root of N times P times 1 minus P, that's your sigma. That's the jump from line to line to fit the normal distribution. So that means I've got the middle. Now I can go 3 jumps to the right, 3 jumps to the left. The percentages never change. 34, 34, 13.5, 13.5, 2.3. Oh, I'm getting kind of scribbly there. 2.35, 2.35, 0.15, 0.15, but the numbers on the bottom do change. So 3,200 in the middle, and then how much does each line go up by? 40, that's the sigma, huh? So this will be 3240, this will be 3280, this will be whatever 40 more than that is, 3320, I think. Just added 40, added 40, added 40. Is that making sense? And then the other way, I'm going to subtract 40. So this will be, I don't know, what is that, 3160? And then, what, 3120? And then 3080, thank you. 3080. Everybody see what we're doing there? So when you do something random, the middle, the mu, is number of times the probability each time. Flipping a coin, half. Rolling a die, 1/6, you know. Multiply that, get your middle. Came out 3,200, put that in the middle. And then your sigma is square root of n times p times 1 minus p. Came out 40, so the middle is 3,200, add 40, add 40, add 40. Subtract 40, subtract 40, subtract 40. Percentages are always the same. Here come the questions. Part B, what does it say? What's the chance that you're going to get between 3160 and 3240? 3160 is right here. 3240 is right there. 34 and 34 is 68% chance. That means, look how predictable that is. If you flip a coin 6,400 times, there is a 68% chance that you'll get between 3,160 tails and 3,200. Okay. Oh, wait, did I do the wrong one? Oh, 3,240. I jumped down there. Yeah, anyway, I did the right thing. So 68% chance that will happen. Do you see how casinos are able to predict exactly what's going to happen? Even though it's random with a pattern. It's a lot of the study now in math science. It's called chaos, randomness within patterns. No, it's not patterns. Patterns within randomness. The randomness isn't as random as we used to think it is. Weather patterns, some of those, these gambling things, there's real patterns in there. All right, next one. Yeah, you could do all the rest. I better move on. All the rest are the same. I'm going to move on, if that's okay. Got a little over 5. We have 5 minutes. Okay. So same kind of thing. So how do you find the mu? It's n times p. N is 2880. Okay. That's the n. But what's the p? What are we doing? This time we're we're rolling an honest die, and we want to get the number 1. So what's the p? What's the probability of getting the number 1 when you roll an honest die? 1/6. Yeah, so on your calculator, you would take 2880 times 1/6, which is really the same as just 2880 divided by 6. If you want to just do it that way, that's okay too. And I'm getting 480. Oh yeah, that's the answer, huh? 480. Isn't that good? 2880 times, you'd go times 1 divided by, you multiply the top number, divide the bottom, right? Anything in the bottom's divided. Get that okay? 480. Now let's do the sigma. So what's the sigma formula? Square root of n. It starts out the same, huh? Np, and then has like a 1 minus p after that. So it's going to be square root of n, 2880, times p, 1/6, times 1 minus 1/6. So I would just type all that into your calculator just like that. Hit the square root button. You should get the square root 400, which comes out 20. On that. Make sure you can get that in your calculator. If in any trouble, hang out after. I'll be glad to help you. Why do they call it an honest die? What's a dishonest die? What are we talking about? Die? Don't lie to me now. What are they talking about, an honest die?
Corner shaped.
What's that?
Corners.
Oh, I never thought about that. Shade the corners. That's good. And they also, the other way is they put weights inside. They put a weight on one side, which tends to make it land down, and the other face will be up more often. You ever seen, old movies where they take the dice after the gambling game and they put them on the scales, and one's heavier than they shoot the guy, right? Right? Because that means there were weights in those dice. they were dishonest dice. So they're saying normal, honest dice. Nothing, no cheating on that one. All right. So once we have our mu and our sigma, then you could do the rest of it, right? You draw the normal curve, put the middle is 480, and every line to the right is 20, and the rest, right? All the rest be the same. Let me look at the last two questions. Well, I need to give you this practice then before we go. All right, so number 10. So here we go. This is like the SAT kind of thing. Anyway, they have this icon they want me to click on. They give you this special little chart to look at. Okay, so here comes their question. They're saying recently 1.5 million college seniors took the SAT, I guess it is. Distribution, normal, bell curve, everything in the world is bell curve. There's the middle, there's the standard. Estimate the 80th percentile. Now, what does percentile mean again? So 80th percentile. What does the word percentile mean? 80% below, to the left. So they want some spot that has 80% below. Well, actually, we just used our little thing here, huh? What am I doing? Boom, there we go. Just use that little formula. Now, they're helpful. That chart just makes it easy. Just use that formula. 80th percentile, mu plus 0.84 sigma. They gave me the mu right here. They gave you the sigma right there. Plug them in, hit the buttons in your calculator. So one of the other ones does the chart backwards. It's a little tougher, but I think you can figure it out. Just run that chart back.